Okay, welcome to lecture 9. So, by the way, we don't have class next Friday because it's a public holiday. So, we don't have class next week. Today, we talk about a mixture of experts, MOE. So, we already studied the GPT-3 the big impact in AI and other different domains. So there was a brief history from GPT-1 to GPT-2 to GPT-3. The key idea is to scaling up. The strategy is easy, but the amazing stuff is how can we effectively scale the model and get better accuracy. GPT-3 has 175 billion parameters. I think that's the key topic in the last 5 years for deep learning and LLM. So in the future, we believe eventually we can achieve AGI. So for AGI, what kind of model do we need? So here is a message from the godfather of deep learning, Professor Hinton. So he believes for AGI, we may need a model with roughly 4.4 trillion parameters. 4.4 trillion parameters. Roughly, you see, so 30 times larger than GPT-3. So GPT-3 is only 175 billion. So for AGI, we believe we need an even much larger model. However, we know GPT-3 is already very expensive. Like between GPT-3, you use 3,000 V100 GPU, you need several months. The model is so expensive, so how can we keep scaling? That's the problem we want to solve. To achieve AGI, we need an even larger model. But GPT-3 is already too expensive. We probably cannot scale in this way. So we need a different way. That's the architecture used in GPT-4. So GPT-4 was published already 1 year ago, more than 1 year. It's March 14 of last year, already more than 1 year ago. So from GPT-3 to GPT-4, so the key difference in the architecture level is GPT-3 use MOE, mixture of experts. So GPT-3 is totally dense, but GPT-4 use a new idea, MOE. In this way, GPT-4 can scale the model at least to 1 trillion parameters. According to Hinton, to achieve AGI, we need 4.4 trillion. At least we should scale to 1 trillion to make it 10 times, roughly 6 times larger. 6 times larger. Eventually, want to 30 times larger. And probably recently you heard of another new model. This model was published by the team of Elon Musk, the #1 rich people in the world. So the model is Grok 1. So it's actually open source. If you like, you can search on Google. They have a GitHub. So for Grok 1, they also use mixture of experts and MOE. So actually another fancy model name is Mixtral. Because last year we know open source Facebook open sourced the Llama model. So some authors from the Llama team they left Facebook. They built a new startup, and that startup, the model of that startup is Mixtral. Also based on MOE. So you see, in the last few years, so many models, so many new models, especially the large models, they use MOE. That's why we study MOE today. At least that should be very important. So why so many fancy models are using MOE, especially for GPT-4 and Grok? Okay. So to study MOE, we need to go back to 2021, the February of 2021, or January. So a model was published by Google named Sweet Transformer. That's the first model using MOE with the transformer. That's the first model. So this work was also proposed by Google. So actually, you see, so even on January of 2021, Google already has a model so large with 1.6 trillion parameters. So even on January of 2021, that's amazing. So the name of this model is Sweet Transformer. So you see, on January 2021, they had a big impact, different media coverage. Like you can check these stories our class. But so here is a screenshot. If you Google Switch Transformer in 2022, you want to know what is Switch Transformer in 2022. Here is actually nothing related to Switch Transformer. So now let me introduce Switch Transformer, and later by Switch Transformer, I introduce the key idea of MOE, and eventually I also show you the architecture of the latest MOE model. So firstly, here is a message, a quote from Google. So what's the idea here? So why do we need a model so large? Why do we need this? Because as I mentioned, to achieve AGI, we still believe we need a larger model. But how can we just use as much as compute as possible and also get a higher accuracy? So we want to make as much compute as possible, because we believe that's the only way to achieve intelligence. But at the same time, can we get actually a better accuracy on some important benchmarks or tasks? The here, the why they want to do this idea still is scaling. They want scaling the model to get a better accuracy. So this message is too long, but you need to pay attention here. So they wanted to have a model easy to understand. That's the first feature. And also stable to train. And also more sample efficient. This sample efficient is interesting. So what's sample efficient? I think you give me the same number of samples or same number of tokens. Between that data set roughly has 1 trillion tokens. Can I get the higher accuracy? I get a higher accuracy? Or assume we are getting the same accuracy. Can I use fewer number of blocks floating point operations? If I can get the same accuracy, can I reduce the computational cost? That's the idea for sample efficiency. So you see, they want to compare to the dense model. They want to compare to the dense model, which means MOE is a sort of sparse model. Today, we first need to understand so why MOE is sparse. Why it is sparse? And then we just want to get better accuracy for pre-training, fine-tuning, and multi-task learning to scale the model to tuning to training. That's the message from Google, why they want to propose a very different model compared to GPT-3. So now, let me introduce the brief idea. Just give you a rough introduction to MOE. So what's the idea of MOE? MOE is a form of conditional computation, which means every step for each token, we just use some parts of the model, not all the model. Like you have different experts, so they have different opinions. So probably here you have 6 experts. You only use 2 of them or 3 of them. You take the 6 experts, they gave us 6 different messages. Maybe only 2 of them are useful or 3 of them are useful. Also, a more relevant will have a stronger voice. We take 2 messages. Which one is the most important message? Which one is the second important message? MOE, the idea is we do not need everything. We need to take the most relevant or most valuable messages. But next time you have a different topic, you may have different combinations. For example, for the first topic, you take these 2 experts message. The second topic, you take these 2. Number 3 topic, you take these 2 experts. It's a random decision. We don't know. We don't know which token is best for which experts. We don't know. It's just a random combination. It's an online decision. It's a decision at a runtime. So now let me explain why we want to do that. Why this is important. We know now the model is becoming larger, and also the data set is becoming larger. So I hope you remember for AI model today, the backbone is transformer. For transformer, different tokens, they need to have the pair-to-pair computation to compute the attention store. So if you increase the model size and the number of training samples, the training cost has a roughly quadratic. That's great. It makes model larger, data set larger. The growth rate of your cost is not linear, it's quadratic. That's great. That's why we have a Google law in 2020. So we know Moore's law is already very aggressive. Right? Moore's law means the chip, like the CPU, the computation power the computation power doubles in 18 months. But Google law in 2022, the idea is deep learning model size double. It's roughly 4 months. That's crazy. So after the model size double 4 months, so our computational cost maybe just double in 2 months. We just don't have enough budget to do that, to scale that. That's why we need a sort of conditional computation. So the idea of conditional computation actually is very easy, because before MOE, for the regular AI model, for each sample, we assume every parameters of the model can be used, every parameter. Like ResNet, we have 25 million parameters. We don't know which parameter will be used. We assume all the parameters will be used for each image. For GPT-3, we have 175 billion parameters. Again, for each token, all these 175 billion parameters we assume will be used in the computation. That's the idea of active, which means every parameters will be used. Now here is the idea. How about for each token, can we just use 10% or 20% of the parameters? Can we just use maybe 15% of parameters, not 100%? If we can do that, the computational cost may be much lower. That's the idea for MOE. But here's the question. We just use 10% or 15% of the parameters. How about we partition the model to 10 parts? So which part should we use? We use 10%. We have 10 different parts, 10 different models. Which 10% should we use? So we need a gating decision. Gating decision just is to pick the best 10% for us. That's the brief idea for MOE. We just use 10% or 20% or 15% of the parameters, and then you need to pick which part, which 10% or which 15%. Okay, now let's go to the first part, the first technical part. So we know before the transformer, the dominating model for NLP is LSTM. So people use the MOE for LSTM first. But the idea is exactly the same to transform. Let me introduce LSTM first and then introduce transformer. The idea is exactly the same. Before I introduce the part, let me also briefly review the word embedding, because some students asked this question. I think this is very basic, but it's still very important. So here is the idea. So you see, often we have a dictionary. Right? So like you can define your own dictionary. So for here, how about we just have 246 different words in our dictionary. So for each word, so it's a one-hot vector. So each word has a vector with the dimension of the number of words. Like here is 246. 246. So 246 vector. So now the embedding idea is we just convert this one-hot vector to a shorter vector. This shorter vector may be not one-hot. It's a numerical vector. So that's one hot vector. It's just do a matrix vector multiplication. You get a numerical vector. That's a word embedding. Just convert a one hot vector to a numerical. That's very basic. Responsibility. Now let's go to the MOE part. So for MOE here, we know we want to embed MOE in the model. How about we just put MOE inside the LSTM? So here it is different step by step. So normally, so this part is just multi-layer step to feed forward there. How about we just change it to MOE? See, that's MOE. So now for each token, we have n experts, which means we have n models. Like n can be 100, n can be 2000. How about n is 100? So we just pick two experts. So for each x, we just use two experts to do the computation. You see now we only use, assuming we have 100 experts, we only use the 2% of the parameters here. We only use 2% of parameters here. That's why it's so efficient, especially for the very large model. That's a brief visualization for. Any questions so far? So again, to pick which two actors should we use, we need a gating function. So here we have a term of sparse here. So why it's sparse? The idea is you have 100 experts, which means the output of gating function is a 100 dimension vector. In this 100 dimension vector, only two elements are non-zero. All the rest remaining 98 elements are zero. That's why it's sparse. That's why it's sparse. So that's also the idea. So why some people believe MOE is a sparse model. As sparse, which means you just use maybe 10% of the parameters. 90% of the parameters are zeros, essentially, for computation. Because we didn't use that, they are just zeros. So now MOE is used once for each position. So here each position, a position means a token. For each token, for different token, for each token we select the best combination. For example, the token 1, you select number 1 and the number 13. For the second token, you select number 14 and the number 21. For number 3, you select number 52 and the number 64. For every different tokens, you just select different combinations. And also, it's a runtime decision. It's not a predefined. It's a runtime decision because this runtime decision is computed runtime by the gating function, the gating network. That's the rough idea for MOE. So let me also briefly review the history of MOE. MOE actually has a very long history even before deep learning. Not just before transformers, it's even before deep learning. So some early research, even in 1991, also SVM, Gaussian process. If you like it, you can check these papers. It's just a history for MOE. And they also use MOE for some important applications. The key idea is just to use different experts for different data, because we believe different experts, different combination experts, they can capture different level of information. That's MOE. By the way, you can also use idea for even seeing, like for even seeing layer. You can build many different kernels. For each map, you use different kernels. You can build 100 kernels for each map. You use maybe 4 kernels or 6 kernels. Different images, you use different combination of kernels. You can use the same idea for CNN. I feel like you can have this kind of project, MOE for CNN. By the way, the TAs. So anyone in research, like build different kernels for CNN and for different images, just take a different kernels. Use MOE idea for CNN. Have you heard? No, yeah. If you like, you can try. That's possible. So, okay, now let's go to the technical part. Firstly is the sparsely gated MOE. The sparse, which means we just use some of the experts, not all the experts. So here, you just pay attention to this equation. So here, Gx is output of the gating function. So Ex is the value for different experts. So like here, you see, so the output of MOE is Y. How about we have n experts? We have n experts. Let's make it very easy. So if the gating function, the number I element of this gating function output is 0, that means we do not need to compute the corresponding action, because we're going to use it. So here, clearly you can see Gx is an n-dimension vector. Gx is n-dimension vector. Ex is also n-dimension vector. So each element of the Gx is a decision for this expert. N means you have n experts. So each element of Ex is also a result of a computation of the experts. We can use thousands of experts, but we may only use maybe 10 or 20 of them. Okay. Actually, this page has all the information, kind of a summary of this lecture. To make you have a better understanding about it, let me give you a very specific example. Yeah. So here I just give you a very naive or toy example. Just want to show the idea. So how about the input? That's our input. Input 1 to 1.5, 0.5. We just convert the token to something like that. X is a token. How about for x plus 1? That's a parameter. That's x plus 2, that's a parameter. That's x plus 3. Now we firstly compute the score for different experts. Just I think I want to make this example easier. It's just linear. It's just modular. So it's bit more in the network. And then we use Somax to convert the scores to weights. We know now. So we want to why we want to use Somax, because we want to make sure their sum is 1. Because that's corresponding to each expert's importance. And now we can get the weight for different experts. And also we can compute each expert's output. Now we just multiply them together. That's the brief idea. Now you have 3 experts, and for each input token, what's the output? So here you see, you use all the experts, but different experts, they have different level of importance. Because we use the Somax. But later, let me show you how can we remove some experts. Now here, we just assume we use all experts. Different experts have different level of importance. But eventually, we only want to use only maybe one part. Let's go to the lecture and then go back to this example later. So that's a brief summary for MOE. How can we do the computation? Now, let me also introduce a very early work by Professor Michael Jordan, not as an MBA staff. It says machine learning researcher, Michael Jordan. So here the idea is they use Somax for MOE here. Again, so this is our input token. WG, just our gating network. WG gating network. So you see, so here is the vector matrix multiplication. X is a vector. WG is a matrix, which means the output should be a vector. Vector, the number of elements of this vector should be the number of experts. That's why it's a vector matrix multiplication. Now, we use Somax here. Why do we want to use Somax? As I mentioned, because we want to make sure the sum of these different elements to 1. So we want something like that. we want something like this. Make sure their summary is 1. Make sure their summary is 1. Make sure the summary is 1. Because it's a combination. It's a combination. But to be honest, frankly, so max is not necessary. Just want to make it easy for computation or make it more stable. Actually, you do not need that. So max, you like. So here is the idea why we use Somax. Now, after we have the very basic MOE, now let's add 2 more components to MOE. Firstly, we add Gaussian noise. So why do we need a Gaussian noise? Because we want to make the model stable, robust. It's just a commonly used machine learning trick. And then we want to just keep the top k elements. How about the n, the total number of actors is 100. K maybe just 10. We just want to the top 10 experts because we want to save computation, to reduce the computation cost. So how can we just keep the top k? That's the value of Somax. We just need to set other elements to minus infinity, right? If it's minus infinity, if it's minus infinity, so the Somax, after Somax, the gate value should be 0. That's why we need the Somax. In this way, we can remove some experts from the computation. That's the idea. So how can we do that? So here the soft path. That's not important. That's just something like a ReLU. That's a better version of ReLU, because the ReLU at 0 point ReLU is not smooth. It's like that. This function is smooth all the regions. That's just something like value. No spiritual meaning here. And that's the noise. That's the noise. And then we just add the noise to the gating network. And then we use Somax. We use Somax. How can we use Somax? We have the keep top k. This function is very easy. The function just just only keep the top k elements of this vector and set all the other elements to minus infinity. That's how we finish the implementation. That's a very important algorithm for MOE. It's noisy top k gating. So now, because only top k elements, they have the non-zero gradients, right? Which means only top k vectors will be updated. That can save more computation in the backward propagation. This is important You see, so only top K experts are used, and only top K experts are updated, which means only top K experts are becoming better. Other experts just the same. Only K experts are becoming better. So that's why we have another issue. This issue is load balance. Let me explain the problem of the load balance. Now, let me give you an example. I want to make it as simple as possible. How about you have 100 experts? Each expert is very large. Each expert has 50 billion parameters. You have to use 100 machines or 100 servers to host the 100 experts. So one expert on one machine, or one laptop, or one desktop. Now, about every step, you just take 2 experts, which means you only use two machines. So that can be a load balance issue because you see only top K, only 2 experts are being updated each iteration. So they are becoming better. For next iteration, they have a better chance to be selected. So eventually, maybe every step, these 2 experts, they have a 90% chance to be selected. Which means you have 10 machines, 90% of the time, only 2 of them are being used. So 8 machines or 80% of machines are being wasted, idle. We have this load balance issue. So how about you have a batch of data? You have a batch data, maybe you have a better chance. Still you have 10 machines. I just mentioned for the 10 machines, two experts, two machines, they are very good. So even the byte size is 10,000, even the byte size is 10,000. Probably the 2 machines can get 7,000 of experts. All the other 8 machines, they only get 3,000, which means these 2 machines, they are overloaded. So other 8 machines, they don't have too much work to do. So other 8 machines, maybe they only need 1 hour to take a computation. These 2 experts, 2 machines, they need 10 hours to finish the computation. But the total computing time should be 10 hours, not 2 hours, because we have to wait everyone to finish to go to the next step. This load balance issue is very bad because a lot of resources are idle. We cannot make a full use of that. I think that same idea in the hospital. Right? In the hospital, for example, you have 100 different doctors. Maybe 10 doctors are very good. So all the people go to hospital, they want to see these 10 best doctors. These 10 best doctors, they actually see people every day. They are becoming even better, and they are becoming better. Other doctors are the same. So they conductors are being more popular. So they conductors, they are very busy every day. Other 90 doctors, they don't have too many patients. Same idea in the hospital. That's the load balance issue. Now, how can we solve this problem? We need to have a second loss function. So how can we define this loss function? Let me define a term here. This is the importance of the batch of the data. Like we have different tokens. For each token, we have a different combination of experts. How about let me give you an example again. This is an example. How about we have 4 tokens? That's the decision for the we have 4 tokens and 8 experts. We want to pick 3 experts for each token. That's the first. That's the getting decision for the first token. That's the getting decision for the second token. That's the getting decision for the number 3 token. That's getting decision for the number 8 token. How about we add them together? Just add them together. We add them together, and that's this important. That's an important function. Right? How about you see, if the number of tokens is very large, eventually you get different values for different experts. Maybe you just add everything, add a lot, and you may get something like this. Hopefully, you get let me just give you a random sample. But maybe you can just get something like where the like is. You see, so this actually the very load balance situation because they are close to native. But normally we don't have something like that. Normally our situation is something like this is 5. This is roughly 10,000. This is just 1. This is 8, roughly 900. This is about a very aggressive number. Yeah, we may have a situation like this. This is a very load imbalance, load imbalance. We want to solve this problem. So how can we solve this problem? We compute the CV. CV here is the coefficient of variation. If you like, you can check this. The definition just the standard deviation, the ratio of the standard deviation of this and to the mean. Right? That's CV. So we just compute the CV of this vector. Compute this CV of the vector to hopefully to minimize the CV, to minimize the variance. I mentioned the idea is just the variance of this vector should be very large. So you see, this is only one. This is only one. It's only 5, and that's a huge number. We want to minimize the CV of this vector. We hopefully after we minimize, we should get something like 1992, 94, 83. That's the idea. How can we achieve load balance? So we just adding this to the loss function to minimize the CV of this importance vector. So, any questions so far? Okay, so now we have a second problem. So this loss function is good in most of the situations, but in some situations, this loss function actually is not good enough. Because even we can achieve a balance here. Here is the trick. So maybe one expert, they get many samples, but with a very small weights. The idea is maybe the weights of this. Sorry, it's not here. It's the weights are different parameter. So because the importance is sort of weights and also the number of received sample. So two situations. The first situation is vectors has a large weight, but a very small number of samples. Second situation is a small weight and a very large number of samples. In these two situations, they may have the same importance. So in this situation, that's not effective for loss function. But the loss function maybe also get a low loss score, but it's not load balance. We need to solve this problem. How can I do that? So here is the second loss function is the load based loss. This is a little annoying, but let me explain them carefully. So we define different term here. So the most important term is this load x. We want to compute a number for and for each item for a batch of data. So this is a vector. The output of this one should be a vector. This vector, the number of elements is n is number of items. So how can we do that? So we firstly define pxi. So what's pxi here? So pxi is the probability of gxi is non-zero. We know gx is the gating decision, right? Gating decision. So as this number I expert being used for x token, so gxi should be non-zero. Now, how can we compute this pxi? Actually, it's easy because we just want to pick the top k we just want to keep the top k experts. We can just do a computation to rank them. That's pxk just hxi larger than the case, the number k rank elements, excluding itself. That's just the idea. Because we only want to take top k experts. We do some computation and rank them. The probability of this expert being used is the probability this one is larger than the number k, excluding itself. That's the idea. So, any questions so far? So we do some computation. Use the computed score to rank the different experts. I want to use this experts. This expert should larger than the top k elements by this score. Okay. So in this way, we can have our loss function. In this way, we can just compute the pxi. So again, soft path is just a function like a value. This is the CDF, cumulative distribution function. So if you like, it's just a way to convert a number to a probability. Yeah. To make it easy to understand, although we just go to show visualization. See, we just convert the number to probability. You see this number is larger, you have a higher probability. That's just the CDF. I hope you still remember. It's actually learned in college year 1 or year 2. So in this way, we can build our loss function. Now, so this this load vector is go back to here. So in this way, we can use just this score to add different tokens to have this load vector, and then we compute the CV of this load vector to add this to the loss function. You see, we just add for each token, right? For each token, then add them together to this load vector. Actually, just like this, to add them together. That's the different P. The P for first token, P for second token, P for number 3 token, P for number 4 token. We add them together. That should be the number should be very close to each other. That's and then we compute the CV of them to add to the loss function. Please.
Sorry, what exactly is the load X function?
Okay. So this is a vector, right? This is a vector. And we want to compute the CV of this vector, to minimize the CV of this vector.
But what is load x? Like what's the function?
P, right? So P for different, yeah, right. P here.
Oh, sorry.
Okay. Yeah. That's P for the first token, P for the second, P for the token, P for the. So just the same idea. Okay. Yeah. So in this way, we can have the second loss function to achieve load balance. Now, let me show you the results. We learned the two loss functions. That's the first loss function. That's the second loss function. And we gave different hyperparameters for these two different functions. Actually, we can use them together. So we set W importance is 0, which means we do not use this function. If W load is 0, we do not use the load-based function. How about we just set them as 0? Test perplexity, which is loss for lower is better, is that accuracy. Lower is better. And so you see, we compute the CV of the importance vector. This is very large, which means it's not load balanced. This is also very large, it's also not load balanced. We compute the ratio between maximum of the load vector and the mean of the load vector. You see, it's a quiz number. It's roughly 18, which means it's a very load unbalanced. Probably the largest number is 18. Maybe many elements just 1. Right? Of some elements maybe 0.1 because it's mean. It is mean. And the second situation, we just use importance-based loss function. The importance-based loss function. We do not use load-based loss function. Now we can get a better accuracy, see better accuracy, and we achieve a much better load balance because the CV score of the importance vector is very low. The CV score of load vector is also low. But it's still not very low balanced because the ratio between max and mean is still roughly 1.5. How about the way number 3 option? We just use the load-based loss function. The accuracy is also good. Now you see the CV of the load vector is lower. Actually, the load balance is also better. For this one, we want this column to close to 1. But if it's 1, it should be very, very low balance. We want this score to close to 0. This score also close to 0. We want this column to be low, the lower mean, higher accuracy. And another different choice is we use both of them. We take W importance as 1 and take W load as 1. Also, we get a good accuracy. The CV of the importance vector is very, very low, which means load balanced for this CV loss. And also load balanced for its load loss. And this is the closed one, which is a perfect, almost a perfect load balance.
Why does the balance of the load affect the accuracy and not just like the training?
Okay, yeah, very good question. Yeah. So I believe you achieve load balanced, the model is balanced, right? So different actors, they can all contribute. Because it's not balanced, only maybe two actors are updated each iteration. It's very biased.
In practice, would all of the experts be like trained from scratch, or would it be like a trained expert model?
I think both of them should work. But if you want to do something fancy, it's a big engineering project that should be done from scratch. Yeah, by the way, the T. So the Victor model, the Llama fellows, Llama folks, the Victor model, do they different from scratch for all the actors?
Yeah.
Yes.
Yes.
Okay. Yes. Yeah. So here now I just show you the performance of MOE. You see, so I just explain the table, and for other tables that are here are similar. So you see, so that's the best results before MOE. That's small MOE. That's just a regular MOE. That's a large MOE. Different situation. We just train this for a short time. Train this for some time. Train this for long. So you see, for different accuracy, you can see the budget is higher for MOE. We get a better accuracy. Also, here is the number of parameters. MOE has a very large number of parameters. See, before MOE, it's only for LSTM, it's only 150 million. So here is actually 4 billion parameters, and that's the operations per time step. That's interesting. You see the interesting pattern here, right? So here the number of parameters is roughly 30 times larger, but the number of link operation is roughly the same. Do you know why?
Because of the gate, because
because maybe only 3% of experts are being used. Only 3% of the parameters are being used. Okay. Also, you see the training time. This one is even faster for 10 apples. So here the key flows per GPU. That's because MOEs kind of have a higher level of parallelism to make it friendly for GPUs multi-threading. That's why we need MOE. Also, I think the most important thing is MOE can get a better accuracy. You see, you increase training budget to get a better accuracy. See, the accuracy is better. Also for MOE for translation. Yeah. So these just different results. You can check after the lecture. Yeah. I also have some slides for review the transformers, but probably we can skip this part. I assume you already know transformers very well. How about we go to the final part? How can we use MOE for transformers? So for the second part of this lecture, let me just use Google Slides because Street Informer was published by Google. I just use the Google Slides to show you how they use MOE for transformers. So this figure is also from Google. This figure was made in 2021. Right? So you see, they already have GPT-3, but they do not have GPT-4. So actually, even before June of 2022, that was GPT-3 time. So Google already has MOE more than 1 trillion parameters. You see, the LTM version of MOE only roughly 130 billion parameters. That's GPT-2. So from the figure, you can also check the before 2017 LTM was still the most popular architecture. Yeah. So why Google want to build this MOE project? Because they want to build a universal language learner. They believe so. No matter you speak Japanese, you speak Chinese, you speak English, speak French, we should have something in common. That's the general language pattern. So they want to find a very good learner. This learner, they believe, should be built on top of MOE. That's why they want to start this project. And another motivation is for Google translation. Today, we have some popular language like Spanish, French, Japanese, German. You have lots of training data. But there are other minor languages, or we don't have enough people to speak the language, so we don't have enough data to train the languages. If we don't have enough data to train the language, probably in the future, our ChatGPT 7, ChatGPT 8 do not have a good performance. That's unfair for the minority. Right? So that's why Google wants to do that. So they show us some data. So today in the world we have 7,000 languages and 2,000 African languages, and also 700 Native American languages. I think in Southeast Asia we also have many different languages. Probably this project also shall be meaningful for but for Google Translate, they only support roughly 100 languages. So they want to support all the languages. And the motivation number 3 is they want to test the scaling law. That's always the most important topic in the last 5 years. We scale the model, we use more computation, we hopefully make the model get closer to AGI. That's to test the scaling law. So yeah, and also they give this fancy topic for research. So they also show us a very interesting picture here. So how many parameters in animal? How many parameters in animal brain? How many parameters in human brains? So you see, that's just food of life. That's cat, and that's human. So human, according to this Google, human has roughly 1,000 trillion parameters. 1,000 trillion parameters. So CAD has 10 training parameters. Now we see the machine learning models. So ResNet roughly 25 units, like fruit of life. And G and MT roughly 20 unit. Transformer 400 unit, just like a honeybee. And GPT 3, 175 billion parameters. So should be somewhere here, something here. The GPT-3. And so 3 transformer is still here. It's roughly 1 trillion parameter, or GPT-4 also 1 trillion parameters. So that means human brain is still 1,000 times larger than GPT-4. That's interesting because in the beginning of the lecture, according to Jeff Hinton, so AGI just need 4.4 trillion parameters, but human already have 1,000 trillion parameters. That's interesting. Now, let me just show you how can we use MOE for transformer. Actually, that's super easy. We just replace the feed forward layer to this. Like we know that's regular transformer, right? That's a regular transformer. We have a block like this one, feed forward network. We just change this feed forward network to n different feed forward networks by MOE. Like n is 100. You see, we all have a big N here. Big N is number of layers of transformer. Like big N is 40. Big N is 40, so big N over 2 is 20. Just repeat this 20 times. We repeat this 40 times. Exactly, we are changing this one to this one. Just change the feed forward network to MOE. This MOE is made by 100 axes, right? 100 feed forward networks. Maybe 200, maybe 300. Any questions so far? Yeah. And then we need to have a gating function. By this gating function, that's our decision. That's MOE's problem. Just multiply them together to give you the output. Yeah. That's the overall architecture. So that's transformer, and then we change to MOE. Here is MOE. Now, for here, you need to pay attention to here. Because this model is too large, we need to put different parts to different machines. So you give me a sample, a token. I don't know which machine the token will go to. I don't know. It's a runtime decision. So you have 10 different tokens. I don't know any of them go which machine. Like it's O2O communication. Everyone can go to everywhere. O2O communication. Like you have n machines, you need n square message. The cost is very high. Okay, that's just a brief idea for MOE. They also achieve a good performance. Again, let me explain this picture for you. So you see, we have 3 different models. This is 37.5 billion parameter. This is 150 billion parameter. This 600 billion parameter. You see, this is 4 times. This one is 4 times larger than this one. This one is also 4 times larger than this one. At the same time, we also increase the GPU cores by 4 times. We increase the models by 4 times, and also increase the machines by 4 times. Normally, we should keep the training time the same, right? We increase computation 4 times, we increase the machine computational power 4 times. But because of its sparse computing, our training time is becoming lower. You see, our training time is becoming lower because it's a sparse computation. And also, we get a better accuracy. Now, let's review this example again to give you an overview for MOE. So for any input token like this input token, for each expert, we have the weight and bars. And firstly, we compute the score for different experts, and then we also max and to compute the importance, and then that's the output of each experts for each expert, and then we just multiply them together, get the final result. So any question for this example? So as no problem, so I have a problem for you. Okay. Now how about let's have 3 minutes 3-minute testing. That's the mixture MOE. Now I give you all the information. The dimension is the number layer. That's height dimension. That's hidden dimension. That number of heads. That's the KB head. That's the context length. That's what characterizes the number of experts. We only use 2 experts for each token. Now, this computer, how many parameters encoded in this model and how many active parameters, which means how many parameters are being used for each token. It's 3 minutes. Okay. Anyone want to share your answer? Anyone want to share the answer? Okay, sorry, we don't have enough time. How about I just show you how can we compute? Yeah, I hope you remember this because we studied this in GPT. So firstly, how can we compute the number of parameters for multi-head attention? Yes, it's just 4 times d model by d model. But you need to know how can we get this 4 times d model square. And for the regular feed forward network, that's how we compute the number of parameters. Just 2 times d model by d feed forward. Yeah, we studied this in the GPT lecture. I will remember. Now, for this mixture, so a little different as a feed forward. They have 3 different parts. The N feed FC up, so that's FC up layer, and also they have a FC gate layer, and also a FC down layer. That means they actually have 3 parts. They have 3 parts. Okay, probably I need to mention this for the testing. I'm sorry. They have 3 parts. And now let's just compute the MOE conditions. MOE just N feed forward multiplied by X plus the router. So the router parameter we know it's just a minor for all the parameters. So the mean part is just is this one. Now let's do the computation. Firstly is the attention. Attention we know is 4 times d model by d model. D model now is 4K here. And the second is the experts. Now experts, we go back to here. It's 3, right? 3 by number of experts. Number of experts 8. So that's hidden dimension by 3 by 8. And we need to multiply that by the dimension. Because it's D model multiplied by DFF. D model is 4K. DFF is this one. About the active. So active, it token use all the attention parameters. This part is the same. The difference is that K N expert K, that's it's 2. We compute we have a 13 billion, that's 47 billion. Okay, any questions so far? Okay, good. Yeah, if you have more questions, you can also ask the team after the lecture or next week. This is very important if you should know the details. Yeah, the lecture also use a load advanced function. Do you understand? This part is important. Please.
Why not put the MOE in the attention?
Oh, why not put the MOE to the attention? That's very, very good question. I believe so attention part is already too computationally intensive. If put the too many attention, that can be a huge cost.
Wouldn't you be able to reduce the cost if you have?
Yeah, but because it's O2O communication, remember O2O. Yeah. Communicating costs can be too high. But later, probably can. LT have different answers why don't we put the MOE for the attention part.
I think G-Sharp paper has tried with MOE attention, and they found that it is very unstable for training.
Okay, yeah. The second is really very unstable. Okay, good. Okay. Any other questions? Okay, that's it. Thank you. Thank you for this time. You have a question? Okay. Questions? Okay. Okay, we come back in 3 minutes for tutorial.